Hi everyone. In this video, we're going to talk about the intro to work via an experiment about springs where we can analyze a force versus displacement graph. So some things to know are the words stretch, spring constant, energy, and then Hooke's law. Now, why are we starting our conversation about energy by looking at springs? Well, it's because the study of springs or other elastic materials provide a good introduction to the study of energy. We can identify some traits of springs by exerting a force on a spring and measuring its stretch. And this is what we were doing in experiment 7. So to kind of recreate what that experiment looked like, we had a spring attached to a wall. So there's my lovely spring drawing. And that spring was like some length. And it really could have been any length. It doesn't matter very much. We'll call it length little l. And what we did is we applied a force to said spring. So that's what that spring looked like afterward. And it was after we applied some kind of force F, right, on this end. So what did that do? Well, it caused our spring to stretch, right? So our spring is much longer than it was before. Perhaps we would call this like capital L. And the thing that we would be interested in taking data about is how far that spring stretched, right? So what's the difference between where the spring originally was and where is our spring now? Okay, so this, which I'm going to denote as X, is our stretch, okay? And our stretch is equal to the length with our force applied minus our original length, okay? So that gives you a good idea of like, this is what we mean when we talk about the stretch of a spring. Okay. So what did we do in this lab? We took a whole bunch of data about where we applied forces to springs. We measured that in newtons. And we measured that resulting stretch, which is often called the displacement of the spring. Okay, and what we end up getting is we get this linear relationship between these two things. And whenever we have some kind of graph, we always want to look at things like the y-axis of the graph, the slope of the graph, the area of the graph, because these are the three components of a graph that are going to yield important information for us. So if we just look at the y-axis is telling us about the force that the spring is exerting. Okay, so we had to pull on the spring in order to deform it and make it stretch. But Newton's third law says that that spring has to be pulling back on us. So how hard the spring is pulling back is being shown here by reading our y-axis. Okay, we're figuring out how much force that spring is exerting. Now the slope is very interesting because, we know that slopes always tell us something that was kept constant in the lab. And in this case, that constant is called the spring constant. And so you may be asking yourself, well, what is a spring constant other than just something that we kept constant in the lab? Well, spring constant is really a measurement of how easy or hard it is to stretch a spring. And considering we use the same spring for all of our data collection, then how easy or hard it was to stretch that spring should have stayed constant throughout the lab. Now, if we have some very large number as our slope, well, that's telling us that this spring must be really hard to stretch, right? Because that's telling us if we have quite a steep slope on this graph, right? That's what these high numbers for spring constants would be describing. They would be describing like a really steep slope to this graph. What that's telling us is that in order to achieve a certain displacement, we would have to exert a huge amount of force to make that happen. Okay, so that would be really describing something that's really hard to stretch. Whereas if our spring constant is very small, well, then that is telling us that this spring is relatively easy to stretch, right? Because if we have a small spring constant, that's telling us that this slope of this graph is relatively small. So to get a similar displacement, then we would have to exert a much, much smaller force to achieve that. Okay? Other things to know is that the shorthand variable letter for spring constant is a lowercase letter k. So we could say that this spring constant, right, it's k. And then the other thing that you should know about spring constant is that the units used to measure spring constant is a Newton per meter. And that's really coming from the fact that this spring constant is being represented by this slope. And since slope is y over x, then we should take the unit of the y and divide it by the unit of our x in order to get the units of this spring constant. So it is newtons per meter. Okay. And that brings us, right, so that was all about the slope. But we still need to discuss what does the area of this graph tell us. And so if you recall, area of a graph is the shape that is bound between your line and the x-axis. So if I kind of draw in the shape here that is generated by my line in the x-axis, then what I'm getting is I'm getting this triangular shape. And as long as I can find the area of this triangle, I will be able to calculate another very important quantity, and this quantity is the energy stored in the spring. Okay, so this is how this study of behavior and traits of springs can link us back to the study of energy, because energy can be found by finding areas of a force versus displacement graph. Now, then the question becomes really, what is energy? It's a little bit weird, right? When we try to think what is the strict definition of energy. And the strict, very academic definition of energy is the ability to do work. Which in and of itself is not a particularly descriptive definition. First of all, we have to know what does it mean for something to do work. And that's not immediately obvious to us. So another way to try to think about energy would be just to think of it as a way to describe how things change and move. Right? In this particular lab, we had energy in our spring when we changed its shape. It went from being one shape to another shape, and when we changed its shape, all of a sudden it was able to store all of this energy. Things can also be moving, and when they're moving, they have energy. The location of an object can lend itself to having energy. There's a lot of different ways for an object to have energy, and a kind of general way to think about it is to think about energy as how things can change and move. Now, that really does bring us to the fact that energy comes in different forms. So how we think about energy stored in a spring is different than how we think about the energy associated with something moving. Okay, so we'll talk about that in section 4.2. What are the different forms? Now, ultimately, we're still kind of dancing around a good idea of what energy is. And that's not because I'm trying to be difficult or anything. It's just because, honestly, if you get down to it, even talking to professional scientists, they're going to tell you that we don't necessarily have a strong idea of what energy is. But we do understand that if we can keep track of energy, so if we use energy almost as like a bookkeeping system, if we can keep track of it as it changes its form, if we can keep track of it as it gets transferred from one object to another object, right? If we can just kind of keep notes on all those things and make sure we know where that energy is and what object possesses it, then we actually have a really, really powerful tool that allows us to make predictions about how those objects will move. Just because we can't necessarily see this energy or taste it or visualize it or anything like that, doesn't mean that we can't still use it as an incredibly powerful tool. So what we can do, right, is we can always be able to calculate energy. Oh, by the way, the unit for energy is the joule, which is usually just abbreviated as a capital J. Now, if we wanted to, we can always look at a force versus displacement graph, calculate this area, and now you will know how many joules of energy a particular object contains. However, we don't always have a graph that is easily accessible to us or provided. And so instead, we can calculate the energy stored in a spring using an equation. And let's see, so energy stored in a spring has the shorthand of U sub S. The capital U stands for potential energy. I know, why did they use capital U? But the subscript of S stands for spring. And this equation is 1/2 times the spring constant times the stretch squared. And this equation really does just come from finding the area of this graph. Okay, so finding the area of this triangle yields this equation. The last thing that I want to touch on in this section is the straight line part of this graph, right? We have a straight line here, and we know a lot about this straight line. We know what the y is, we know what the m is, we know what the x is, we know that our y-intercept is 0. So we can write the equation for this straight line. And the very first person who did it was a guy named Robert Hooke, who was an English scientist. And he got this equation for this straight line named after him. So we call this Hooke's law. So again, it's going to take the format of y equals mx plus b, since it's just a straight line. And since our y-axis was the spring force, then we're going to start this with spring force. I do have absolute value bars around this because Hooke's law is not going to give us any indication of direction. It's only going to give us indications of magnitude. So even on the equation sheet, they're going to put absolute value bars in 2 different places. Anywho, so this is our y, and our y equals mx plus b. The m is spring constant, so I will write spring constant in here. And then the x is displacement. So this is where the other absolute value bar comes in, is with that x. And we don't have to have a plus b because there is no y-intercept on this graph. And so this equation is going to allow us to calculate the spring force or the force exerted by a spring in any situation, as long as we know the spring constant and we know how far this spring has been stretched. And both of these equations that I've circled in red here, the equation for energy stored in a spring and the equation for force exerted by a spring, are both on the AP Physics 1 equation sheet. So you guys will be able to reference these during the test anytime that you like.